Okay, good morning, and thanks for all being here. So, after getting this invitation, I decided rather than focusing on kind of one work in probability, I want to give you several examples of an approach that has been useful for me. Hopefully, it can be useful for you, which is seeing connections between different areas, either within probability or adjacent areas that use probability theory. And so I will give 3 examples, necessarily not going into all the details in them. And these are examples I've worked on over the years. Some of them are not recent at all. So one example I'll tell you about is intersection equivalence. So that is something I worked on 20 years ago. Then one example is, second example would be broadcasting on trees, which I've worked on also some time ago. And then something more recent from the last 5 years, which is still developing, which is the connection between cover times and Gaussian process, specifically the Gaussian free field. So these are different examples, but the common theme is in all of them, a lot of the progress is made, not only by trying to work hard and solve a hard problem, that's always recommended, but also looking, is there a solution of a hard problem in another area that can be useful for the problem I'm interested in? So, so this example of intersection equivalence, let me go back to the background, really to something very, very old. So a theorem of basically of Kakutani and Dub from the 40s, which tells us which sets are hit by Brownian motion. And to be concrete, let's focus on 3 dimensions. This can be adapted to any dimension. So just to be concrete, I want to focus on R3, but so I'm given some compact set A, and I want to know when does Brownian motion, so B will just be the path of Brownian motion. When does Brownian motion hit the set A? So I want to know when does Brownian motion hit the set A with positive probability, and theorem of Kakutani is this is only if A has positive one-dimensional capacity. So if D is bigger than 3, then the 1 you will replace here by D minus 2. And here, so what is the capacity of a set? It's the inverse of the minimal energy. So we take the minimal energy of a measure and invert it. And this is a probability measure on A. And here so if I'm talking about capacity alpha, this will be the alpha energy. And the alpha energy of a measure is, this is called the Riesz energy. So we take d mu x, d mu y over x minus y to the alpha. So these are known as Riesz capacities. When you put alpha here, the case of alpha equals d minus 2 is distinguished and is Newtonian capacity. But okay, and all this can, in 2 dimensions, things are a little more delicate. You have to talk of logarithmic capacity. Let's focus on 3 dimensions. So this is the classical theorem of Kakutani. And So one natural question that was open for many years in the people worked on it a lot in the 80s was, I want the same thing for two independent Brownian motions. So I have one Brownian motion path. Everything is in R3 for concreteness. I have another Brownian motion path B2. These are independent Brownian paths. By the way, just so there is an annoying thing that usual Brownian motion, we start at the origin. So if a set contains the origin, it will intersect it. So I want the set not to contain the origin. Alternatively, it's better to think, and we will do that we start the Brownian motion instead of at the origin. Let's just start it at a uniform point in a box. So I didn't say this in the beginning. Either I have to take A removed from the origin, or I have to start not at a point. So let's do the latter thing. So let's think of the initial point. So B at time 0 will be uniform in some box, say the unit cube. Okay, and then I take B2. It's an independent Brownian motion. So here is B1. And then I have an independent Brownian motion started at another uniform random point. And I want to know, when does this, so it's also very classical that the two Brownian motions in R3 intersect with positive probability. And so there is, I already jumped here. So okay, so then the question is, when is if I intersect these two Brownian motions, so we already know, and this is again a classical theorem of Dvoretsky-Erdős-Kakutani, that two Brownian motions in 3 dimensions will intersect with positive probability. But now I want to intersect with a set A, again some compact set. I want to know, when is this intersection on empty with positive probability? And what is quite easy to show is that it's enough that the two-dimensional capacity of A is positive. So just to get an idea, alpha-dimensional capacity is closely related to alpha-dimensional Hausdorff measure. So if a set has Hausdorff dimension bigger than alpha, then it has positive alpha-dimensional capacity. So if a set, it has to be really bigger than like a plane in order for it to have positive two-dimensional capacity. So this direction was relatively easy, kind of a second moment argument, and was well known. But this direction was open for a long time in the 80s. Various good people thought about it. And already as a grad student, I was very interested in this question. I didn't solve it then. And the first solution was actually obtained. So this is true, but not easy. The first solution was obtained by Fitzsimmons and Salisbury, 89, published in the Analysis Institute Henri Poincaré. Very impressive solution using very nice but quite fancy potential theory. There's a sentence from their paper that I remember. So they consider much more general setting, and which makes it a little hard to read their paper. So they write, we will work in the setting of special standard processes. We won't define them precisely here, but see page 347 in Blumenthal-Gettur. Roughly speaking, these are processes that are left continuous in the ray topology. Okay, so this is just roughly speaking. But in fact, there is a really nice idea in their proof. I won't go into that, but a few years later, I found a different proof, which I want is the one I want to tell you about, which was based on this idea of intersection equivalence. And the point is that a related theorem was proved by Russ Lyons in the context of percolation on trees. And that can be converted to answer this question and get some more. So let's shift gears for a minute, and then we'll connect to this. So so the question, so I want to tell you about Russ-Lyons theorem, which was kind of first published. So 92 Annals Probability is the paper I'm referring to, and you can also find an account of this in my book with Russ, which is about to appear in Cambridge University Press. So you can find some exposition of this theory. But the original papers of Russ are very well written. And what the theorem concerned is the following question. So I have a tree. So it's not a regular tree, it's some general tree. And I'm doing percolation on the tree with some parameter p. So what does that mean? We have, so every edge is open with probability p independently. And then we have some root, and we ask what is the probability that the root is in an infinite cluster, infinite open cluster. And the answer is that up to a constant, indeed, up to a factor of 2, this is going to be the equivalent to the capacity of the boundary of the tree. I'll write the tilde because we're in the tree. And here I want to use the following notation. So I'm going to take p to be 2 to the minus alpha. And so to define the capacity, as I did there, I need to have a metric because we had the distance. So what is the boundary of the tree? The boundary of the tree is the set of infinite rays, infinite paths from the root. And if I have two rays, I will consider the distance between one ray psi and another ray eta to be 2 to the minus, so you could put e here, but I'll put 2 to the minus xi min eta. So what this is the point. If I have the two paths xi and eta, two rays, this is the point xi minimum eta. So this is the root. This is the point where the two rays separate. And this absolute value means the number of edges from the root to this separation point. And this is one of the natural metrics on the tree boundary. And then the rest of the definition proceeds as above. So the alpha energy, I'll put a tilde to remind us that we're on the tree, of the boundary of the tree is just the integral d mu xi d mu eta of the distance between xi. Yeah, I'm sorry. So this distance okay, so this is the d of the integration. This is the distance. I hope that's okay. And we take the distance to the power alpha. Okay, so this is the alpha energy. So this is Lyons' theorem. So again, in this theorem also, one direction is easy to show that probability is at least the capacity as a second moment argument. The other direction needs some kind of a Markov property. So I told you about Kakutani's theorem, and there are many proofs of Kakutani's theorem, but really the reason it works well in both directions is in one direction you just use second moment, in the other direction you use a Markov property of Brownian motion, namely if you know that the probability of Brownian motion intersecting A is positive, then you want to show that the capacity is positive, so you have to find a measure of finite energy. What will be this measure? It will be the hitting measure by Brownian motion of the set A. So you're given the data that the Brownian motion hits A, you want to construct a measure, you just use the hitting measure. And then the Markov property of Brownian motion can be then used to control the energy of the measure. In the tree, so Russell didn't exactly express his proof like that, but later I want to send you to a different paper called Martin Capacity. So it has a longer title, but this is with Beniamini, Pimentel, and myself in 95, also in Annals Probability, where we explained Lyon's theorem in a way which is close to Kakutani's theorem. Namely, suppose you do percolation, and you look at all the vertices that are connected by all. So let's just go to level n and look at all the vertices that are connected by open paths to the root. This is a random subset of the boundary. In this case, we're just doing a finite version of the boundary, so we're just going to level n. But a nice thing is that if you go along this finite boundary of the tree, so along level n, and just jump left to right just along the vertices that are connected to the root, this is a Markov chain. So if I'm here and I'm connected to the root by an open path, then to find where is the next vertex that's connected, what happened to the left is irrelevant because of the tree structure. And this Markov property is really one way to understand what makes the non-trivial direction in Lyon's theorem work. So it's really the connection to that. So anyway, so once you have a Lyon's theorem, the point is that this is an equivalence. And now we want to think about it not on the trees, but in the context of Euclidean space, where there's a natural mapping from trees to Euclidean space, just b-adic expansion, or say binary expansion. So if we have, so let's see, there's the eraser. So if we want to realize kind of a connection between trees and Euclidean space, so you can use binary expansion. In the case of of a cube, we would divide it into 2 by 2. So if in 3 dimensions we get 8 cubes, and this gives a natural structure of a 8-array tree. Every vertex has 8 children. And if I have some set A, let's suppose that the set A is in the cube. So we can always move the sets to the cube. So we can assume that we're talking about sets in the cube. Then we can use the binary expansion to find the tree T. So T is the tree of binary, so let me be TA, tree of binary expansions of points in A. So A is now a set in 0, 1 cubed, compact. Okay, so if we look at this tree, if A was, for instance, the whole cube, the tree would be the full 8-array tree. Every vertex has 8 children. But if A is a smaller compact set, for instance, if A maybe doesn't intersect this cube, then already in the first generation, instead of having all 8 children, I have fewer children, and so on. So just by looking at the geometry of A, which binary cubes it intersects, I can easily build this binary tree. And then once you're in this form, Lyon's theorem can be extended. So now I'm going to look at a random set. So lambda, let's call lambda of alpha. This will be inside the cube. This will be a random set obtained by, or I'll call it a random fractal or fractal percolation. It is obtained by retaining cubes with probability p, which is 2 to the minus alpha. Okay, so I'm drawing two-dimensional pictures, but think of 3 dimensions. So I take the cube, divide into 3, and each of these cubes I retain with probability p. If I remove it, then it's not going to be in my set. Say I remove this one. Now I have these. Each of these I again subdivide, and I retain with probability p, remove with probability 1 minus p, and so on. So this is a classic construction of fractal percolation, but we see that it just corresponds to percolation. If we map it back using binary expansions, it just corresponds to percolation on the tree. And therefore, we can express Lyon's theorem in the form that the probability of the random set lambda alpha intersecting a fixed deterministic set A, this probability is equivalent to the capacity of A. So actually, I should put the capacity of the tree corresponding to A in alpha. So this is just a translation of Lyon's theorem in this kind of setting. This is just the probability that when I do percolation on the tree corresponding to A, I have survival in that tree. So that corresponds to this intersection being non-empty. Okay, and now if I want to think of this, the capacity tilde, if I want to think of it geometrically, it corresponds to a slightly different metric, right? The distance between 2 points in the cube is not their Euclidean distance, but it's pretty close. It's the minimal binary cube that contains both of them. So that's usually like the distance, but not always. If the 2 points are, very close to very close to a boundary, like if the 2 points are here, then their Euclidean distance is small, but their tree distance is large. Nevertheless, there's a theorem that says that the capacity, a theorem proved by Pimentel and myself, that the capacity tilde is equivalent to the capacity of the set A. So although the metrics are not, they're not by Lipschitz equivalent at all, but capacity is sufficiently flexible that one can map one to the other. This argument is really just based on Cauchy-Schwarz. It's not hard. Now, once we have this, then we are in good shape, because now we can state one connection already. Let's see, how are we doing on boards?
Continue here.
OK, good. So putting these together, say, with Kakutani's theorem, we see that the probability that the Brownian motion, say, let's call it just B1, intersect A is non-empty, is equivalent to the probability that, lambda 1. So lambda 1 is, remember, a random set corresponding to the index 1. Intersect A is non-empty. Right, because both of these things, any question, Pascal, is something?
It's just about the board. Don't worry.
Okay, so both of these things are equivalent to the one capacity of the set A. Okay. Have we made any progress? So one thing is, you see that this is what I'm calling intersection equivalence. So the random set B1, the path of a Brownian motion, started uniformly in a cube, is, at least inside the cube, intersection equivalent to this random set, so to this random fractal. So these sets look completely different. Their topological properties are very different, but their intersection properties are the same. Given a deterministic target set, or any target set which is independent of these sets, then to ask whether intersects B1 is equivalent up to constant to ask whether it intersects lambda 1. So why is this useful? Because it's very easy to understand what happens when we intersect two independent copies of this set. So remember, what was our goal? To understand, I take B1 and intersect with B2, intersect with A. And we want to understand, when is this non-empty? Well, let's think of this as some set freeze B2. And now we know that this is equivalent by this to the probability that I'll call lambda 1 of 1. So this one just corresponds to the my parameter alpha, but this one means I'm going to take one copy of the set, intersect B2, intersect A is non-empty. Right, so this means equivalent up to constants. I won't care about the value of the constants now. And this is just applying this fact that we obtained using, but replacing the set A by the set B2 intersect A. So you just condition on B2 and apply the previous thing. Okay, but now use commutativity of intersection. So you can look at this the other way. And this is equivalent to the probability. So this is now B2 intersected with A and this set. So I can now use that same principle again to say this is equivalent to lambda 1 of 1 intersect lambda 2 of 1. So these are two independent copies of this random set lambda of 1. So let me remind you, what is this set lambda of 1? It's very simple. You take the cube, divide it in 8, and each subcube you just keep with probability half and remove with probability half and repeat. So that's lambda of 1. And we have two independent copies of this set. And we're still intersecting with A. Okay. Have we made progress? Yes, because this intersection is easy to understand. I told you about this random set. You intersect two copies, what do you get?
Lambda 2.
We get lambda 2. This is exactly lambda 2, right? Because if I'm taking intersection two copies, it's the same as taking a cube and saying I keep it with probability a quarter instead of a half. So I have lambda of 2, just one set, lambda of 2 intersect A. But now I have Lyon's theorem, or our variant of it, applied with parameter alpha equals 2 instead of alpha equals 1. And we get this is equivalent to the capacity 2 of A. So we get a very soft proof of this Fitzsimmons-Salisbury theorem in this case. Okay, but the intersection equivalence gives you some more information, which was not. So their theorem, although it gives you this, their theorem doesn't actually give you everything you can obtain from these techniques. It does give you, there are some advantages to their technique, there are some advantages to this. So both are useful. The point of showing this example, it's now more than 20 years old, is that if you have a hard problem, well, if you can solve it, great. If not, maybe this problem has been solved in a different language, or keep your antennas up to see, is a problem being attacked in a different area, which is really equivalent to your question. Now, let's see, I didn't put away my clock. So what is the time? Okay, it's 10 o'clock. So we have till 10:20.
25.
Okay, till
Your
10:25.
questions include-
Okay, so I had a nice story about broadcasting on trees. I won't tell it in that kind of detail, but before I go on, any questions about this story? Again, you can. So if you want to see more about this, if you search for intersection equivalence, there's a paper in Communication Math Physics from the 90s. And all of this is also covered, as I mentioned, in my book with Russ.
And there is a third board in the back, so you can
Uh-huh.
push,
Okay. So the second example, which I won't give any detail on, but this is an example which I first heard about from several computer scientists. So one who was then in France and is back in France, Claire Mathieu, also formerly Kenyon, and Leonard Schulman, and also Leonard's student, Will Evans. And they were computer scientists interested in the following kind of question. So you have a bit. Let me put the bit to be a plus or minus 1. And this bit can be, and we have a tree. And the bit can be flipped with probability epsilon. So we have, if I have here some bit or some spin s, here I'm going to get minus s with probability epsilon, and I'm going to get s with probability 1 minus epsilon. So this is true along every edge of this. This is called the binary symmetric channel. With probability epsilon you flip, with probability 1 minus epsilon you don't flip. So you have, let's say I started with a plus. So usually I have a plus, but occasionally with probability epsilon I have a I have a flip. Okay, and so on. Now, this came from a problem in noisy computation, which I won't tell you about, but the question they were asking is, suppose I see the individuals in generation n, and think of n as very large. So I see the spins in generation n. Does that give me information what was the original spin? So of course, this depends on the epsilon. So we started thinking about this problem, but so you may want to think of it first on the binary tree, but we understand it on any tree. Anyway, let me just tell you the answer. I don't have time really to explain the techniques, but the key thing is, so let me explain it for the binary tree. So if 1 minus 2 epsilon is less than 1 over square root of b, then information dies out. So the mutual information between the root and everything at level n goes to 0 exponentially. And if 1 minus 2 epsilon is bigger than 1 over root b, then the information survives. So the mutual information stays bounded below, which means if you see the nth level, you can never be sure of what was here, but you have some useful information that doesn't die out. So this is a paper called Broadcasting on Trees and the Ising Model. And the case of binary trees, it turned out, was already solved by Blecher, Ruiz, Zagrebnov in the setting of Ising model on trees. But we did not just that case, but the case of general trees. So for general trees, replace b by 1 over the critical percolation probability of the tree. And this is actually using some of Russ-Lyons' theorems, one could extend this to understand this process on any tree. The interesting part of the story is it turned out, I have friends in different areas, and I talked to some of my math biology friends, and it turns out this same question was investigated heavily in math biology as a toy model for understanding phylogenetic reconstruction. So you have some mitochondrial DNA, and you see how it evolves through mutations, and you want to understand, given the present population, what can you say about mitochondrial DNA of some ancient ancestor? And there it's really not binary, but this is kind of the first toy model that they were looking at, and they hadn't even, in biology, they hadn't even obtained the sharp result for the Beery tree by that time, although there was some PhD thesis on it and so on. And again, this problem was investigated separately in statistical physics in the context of the Ising model. So making these connections was very useful, because it turned out later that some of the techniques of the biologists, although they were inferior for the binary case, they were very useful for handling more symbols. So Elchanan Mossel wrote his thesis with me in Jerusalem on this topic and continued to develop it further. His student, Alan Sly, developed it more, and this is a story which is continuing. So it turns out that the stochastic block model, which is a very hot topic now, is very usefully approximated by this model. So understanding this is kind of a necessary first step to understanding stochastic block model, and this is a very hot topic which I recommend you to look at, but I can't get into. But the point is that this is really probability, but was investigated by people in different application areas or in different topics without being aware of each other. So just being aware of what's happening in different communities who do probability, even though they're not called probabilists, can be very useful. Okay, so in the last few minutes, 18 minutes, I want to tell you about last thing where, again, a different connection. This will only be a brief survey because of the time. Okay, so this is about cover time, a topic in probability, but it was really studied more by combinatorialists and computer scientists, cover times for random walks on graphs. So what I'm telling you is a very brief survey of work from 5 years ago with Jian Ding and James Lee, and some later developments. So Jian, actually, he did this when he was still in UC Berkeley. Now he's in Chicago. So this is about random walks on graphs, topic that probabilists, some probabilists like, many combinatorialists, computer scientists. And the issue is, how long do you need to run until you cover the graph? And by putting conductances, you can get any reversible Markov chain. Let's focus on simple random walk on a graph. So all the weights will be 1. We're just doing simple random walk. So this is okay, local times and hitting times. And really, the cover time is when we visited everywhere. So just reminders of some notation. So hitting time from U to V is the expected time a random walk started at U will take to reach V. So this is almost a metric. It satisfies triangle inequality, but it's not symmetric. So we can symmetrize it and get the commute time, HUV plus HVU. This is now a metric on the graph, both triangle inequality, symmetry. Now, the cover time, the object of interest here, which again, it's a very natural thing to look at, but computer scientists were interested in it because it is related to algorithms for determining connectivity. So the cover time is just the expected time from the worst starting vertex to hit all vertices of G. Just to give you an idea, here is the order of magnitude of cover times of different graphs. So if you have a path, it's n squared. Complete graph is just coupon collecting, it's n log n. By the two-dimensional grid was determined up to a constant in 89, it's n log squared n, but determining, so by n here I mean the number of points. So this is a root n by root n grid. Determining the right constant in front took a lot of effort. So that's work I did with Demboros and Zeytouni. But I'm not going to be interested in constants right now. So this gives you order of magnitude of cover times in some graphs. And there are some general bounds. Cover times are always at least n log n, and at most order n cubed. Okay, so it will be useful in understanding cover times to use the notion of effective resistance. Many of you know that. One way to think, if you haven't worked with effective resistance, one way to think about it is via the commute time I just defined. So this is a commute time identity, actually first proved by computer scientists, which says that the commute time is twice the number of edges times the effective resistance. So if you want, you can think of this as a definition of effective resistance. There are other definitions as well. And this in particular tells you that effective resistance, it's one way to show that effective resistance is a metric is via this identity. Okay, the triangle inequality of effective resistance is not obvious from the classical definition, but it is obvious this way. Okay. So Aldous and Phil in the 90s asked, can you estimate the cover time of a graph up to constant deterministically? Of course, you can estimate it by running a Markov chain, running the walk, averaging, and you'll get some statistical estimate, which will be pretty good. But suppose you want to know it for sure, deterministic estimate up to a constant. Can you do this efficiently? So this is very easy if you want hitting times, because hitting times satisfy an obvious linear equation, right? Hitting from u to v, if u is different from v, well, I have to take one step from u, and then I have an average over the neighbors of u of hitting from w to v. This is a system of linear equations which is uniquely solvable and gives you the hitting times. Very easy. At most n cubed. But what about cover times? They couldn't write such equations. In fact, you can write equations for cover times in this space of sets, and it will give you some linear system in exponentially many variables. So this will give you an exact solution if you have exponential time. So they asked, is there a polynomial time algorithm to estimate it up to constant? And Kim, Lovas, and Vu, some of the top combinatorialists in the world, showed that you can get a log n squared approximation using what's called the Matthews bounds. So Matthews in 88 proved a nice upper bound. So the cover time is at most the maximal hitting time multiplied by log n. When I have extra, when I give longer talk, I give this proof. It takes just a few minutes, but I won't. So cover time is at most the maximal hitting time multiplied by the harmonic series. But there's also a lower bound, so the cover time is at least following. You maximize over subsets of the vertex set, and then you minimize over u different from v, the hitting time from u to v times the log of the size of the set. And what these people showed is that this lower bound, together with the maximal hitting time, which is also a lower bound, if you take these two together, then they are very close to sharp. So up to a log n squared, they give you the cover time. But it's not up to constant. They gave examples that show this log n squared is really there. So they were motivated by this Aldous-Phil problem, but and they made a lot of progress, but they didn't quite solve it. Now there was another conjecture which also motivated them. This is a conjecture of Winkler and Zuckerman, and it is concerns the blanket time. So the blanket time, so when you reach the cover time, you visited every vertex in the graph, but non-uniformly. Some, right, the last vertex you visited is, you reached is visited once, and by that time, there will always be some other vertices that are visited many times. Even in the complete graph, right, when you cover the complete graph, this is just coupon collector, you reach some vertex once. Most vertices are visited log n times by that period. So they asked for the blanket time, which is when you cover the graph approximately uniformly. Say all the local times are within factor 2 of each other. So here the local time at the vertex is the number of visits to x normalized by the degree. We normalize by the degree because that's a stationary distribution. We know that asymptotically, if I look at the ratio of two local times, asymptotically it must tend to 1. This is just the fact that the empirical distribution will tend to the stationary distribution. But here we're not interested in asymptotics. We want some quantitative bounds. And so Winkler and Zuckerman looked at this blanket time. Again, it's the expected time when all vertices are visited, say, within a factor beta of each other. And they made a very courageous guess. They guessed that the blanket time is within a constant of the cover time. So they made this guess based on, well, very good intuition and about 3 examples. So they analyze, well, they can understand the complete graph, they can understand the torus, that's about it. But then they had the intuition that what happened in these examples should happen completely generally, and they conjecture that the blanket time is always within a uniform constant. It just depends on this beta, and doesn't depend on the graph. Really amazing courage, which turned out to be right. So again, by this, the method of Kahn, Lovász, and Kim actually implies that their guess was right up to a log n squared, because this estimate that Kahn, Kim, Lovász, Vu developed works both for cover time and for blanket time. And so you get that they're within log n squared of each other, but still don't know, that doesn't imply that they're within a constant. Okay, so I was very interested in cover times too, and I worked on them with Martin Barlow, Ding, and Nachmias. We were really trying to understand cover times of specific graphs, Erdős-Renyi graphs near criticality. These are quite delicate graphs. And in order to understand the cover time there, we took the approach of Kahn, Kim, Lovász, and Vu and refined it a little bit, and we got the following general bound, which we applied in the case. So the cover time we could bound by the number of edges times the effective resistance, the diameter and the resistance metric, times some integral. So this is the root log of the entropy number. So you have the vertex set, and you ask n, so what is n of s d epsilon? Given a set S, a metric d, and an epsilon, it's a minimal number of epsilon balls you need to cover the set. And here where the set is the vertex set, the metric is the effective resistance metric, and the and the radius we want to look at is r times epsilon. And you take that for each epsilon, you take square root, integrate, square, and this is a bound for the cover time. Again, this was some of the ideas in this proof were in this Lovász, Kahn, Kim, Vu paper, but we had to refine that a little. We got this bound. We submitted that paper, and we were kind of in a rush. And after we submitted, I was talking to Jan, who was my student. I said, "Wait a minute. This integral looks familiar." So this is very similar to the Dudley integral for Gaussian processes going back to 67. Okay, so this is, there's some differences here. There's a square, the metric is different, but it does look similar. So then maybe now this Dudley integral is a way to bound the soup of a Gaussian process. So what is going on here? So I'll tell. Well, many of you know Gaussian process. So XS is a Gaussian, is a Gaussian process. The metric we use on the Gaussian process is just the metric given by the standard deviation. So the distance between 2 points is just the L2 distance between the corresponding Gaussian variables. And then, so this was a theorem of Dudley in '67, which was almost sharp. So this is usually a very good bound, but it's not exactly sharp. And actually finding the right, the sharp bound took 20 years after this Dudley theorem. And when I saw this, I said, well, maybe for cover time, we don't need to go through the same 20 years. We can just piggyback over on the work on the Gaussian processes. So Fernique-Talleyrand, culminating in Talleyrand 87, managed to find a sharp formula for the soup of a Gaussian process. And that naturally, is this analogy useful? Can we use their theory somehow? So to understand the positive answer, we have 5 more minutes, so we won't really understand it, but I'll tell you a few things. So it turns out the relevant Gaussian process is a famous one, which is important for various reasons. It's the Gaussian free field. This is so Gaussian free field, is studied both in discrete and continuous settings, and I think we'll hear something about it later today in the continuous setting. In the discrete setting, it's given a graph. This is a centered Gaussian process, and the variance of gx minus gy is the effective resistance between x and y. So given a graph G, I know how to compute effective resistances, and then I can build a Gaussian process where this is the effective resistance. And equivalently, if you're used to describing a Gaussian process via its covariance kernel, the covariance of the two variables gx and gy is the green function from x to y for random walk killed at some specific vertex v0. So this just means I start random walk at x, look at the expected number of visits to y with killing at v0, normalized by the degree of y. So this green function is a positive definite symmetric function, and so it's a covariance kernel. And that's the Gaussian free field. There's some pictures of what it looks like in 2 dimensions in a 2-dimensional lattice. And if our theorem, which answered both the Aldous-Phil question and the blanket time conjecture of Winkler and Zuckerman, so it was obtained in 2010, I think they published in Annals Math in 2013, is that the cover time is equivalent, up to constants, to the number of edges times the soup of the Gaussian free field on the graph squared. And this is also equivalent to the blanket time. Okay, so we don't know any direct probabilistic proof between the cover time and the blanket time. Well, obviously, the blanket time is bigger than the cover time, but the other way, we don't know any direct probabilistic thing. It's just via analytic characterizations, we can show they are equivalent. Okay, so that's the theorem. So indeed, we didn't have to wait the 20 years because we could just use some of the previous work. So there's a rich theory of the maximum of Gaussian processes, and I can't go into it, but there is this gamma 2 functional, first described by Fernique and then used by Talleyrand, completed by Talleyrand, to show that the soup of a Gaussian process is this gamma 2. And our main theorem was that the cover time, can be restated that the cover time is equivalent to this number of edges times this gamma 2 squared. And this then allowed us also to find an algorithm to estimate the cover time. The story of gamma 2 is very interesting, but I have to skip it. In retrospect, there are many analogies between Gaussian processes and the random walks that were not really realized before. So, for instance, there is a classical inequality in Gaussian processes called Sudakov minoration that says, if you have a Gaussian process and you have some separated points, then you can lower bound the maximum. And it turns out this is very close to the Matthews lower bound. Okay, so I'm going to skip the definition of the Gauss gamma 2 functional and say that the crucial element of the proof, which also has a strong French connection, is this Dinkin isomorphism theory, specifically a theorem due to Eisenbaum, Nathalie Eisenbaum, Caspi, Marcos, Rosen, and Xi, so at least 2 Parisians there. And this is an amazing theorem that relates the local time of a process to a Gaussian field, and in our case, to a Gaussian free field. Again, no time to tell you anything about that, but that's kind of was a crucial element in the proof, and you know, that's a whole other story. I'll finish kind of in the last minute. One thing that, so we got an estimate of the cover time up to constant, but we wondered, is it the connection actually sharper? Is the cover time asymptotic to the number of edges times the maximum of the Gaussian free field squared? If this is true, then the Talleyrand theory is not precise enough for that because it only estimates Gaussian processes up to constant. So one needs a different technique. And indeed, an upper bound followed from this isomorphism theorem. So the cover time is at most that. But we couldn't, at the time, prove the corresponding lower bound. And this was proved by Jian Ding in a bunch of cases, general trees, and assuming a uniform bound in the degrees. And then and then the general thing was proved by Alex Zhai, based on an idea also, you know, independently found earlier by Lupu. And this is again goes back to breaking barriers. So we're talking about random walk on a discrete graph. But it turns out in order to get the sharpest results, it's better to look at the cable process. So you have the graph, you put the edges, you have the random walk. Instead of doing a random walk on the graph, you do Brownian motion on this metric space obtained by thinking of, you know, the edges as segments. And it turns out that if you apply the isomorphism theorem in this context, it's more powerful than applying it directly on the graph. And one gets the complete, the exact estimate. So this refinement, again, is due to Alex Zhai. You can find his paper on the archive. Again, there's related work, not exactly the same, by Titus Lupu, done in Paris. And that's a good point to stop. Thank you.
Thank you very much, Yuval. Are there any questions? So don't worry, you don't need to talk into the microphone. You can just speak up loudly. So maybe I have a question about the intersection equivalence before. Yes. So you mentioned the Markov property on the tree when you look at the tree from left to right.
Yes.
But if you do it in the Euclidean setting, does this have an analog in the Euclidean setting when you use the dyadic tree? Because you mentioned this Markov property, but I didn't see how if you use it. And
so the point is that it's really so in the Euclidean setting you have this. You know, the cubes have some boundary intersection which creates some, you know, superficial difficulties. But the thing is, we can completely transfer the questions up to the tree, and really solve them on the tree where we have this Markov property. So, you know, roughly speaking, you can think of a Markov property obtained by a kind of random piano curve in space. But really, rigorizing in this format is much more painful than it needs to be. You just transfer the question, you know, the question you have to the tree, and there, kind of the nice separation you have in the tree yields a very clean Markov property. So everything, you know, so you do infer any consequences you want in Euclidean space by mapping to the tree, rather than working directly in Euclidean space. There is some cost to this approach. For instance, if you're looking at high dimensions, you lose constants that are exponential in dimension. So this is not a good approach for kind of high dimensional uniform estimates. But many questions we care about are in 2 and 3 and low dimensions. This has an analog in 2 dimensions. In 2 dimensions, you have to vary the percolation probability as you go deeper. But so everything works just transferring to the tree.
Are there any other questions? So if not, we thank Yuval again.